So we're going to look at examples 4, 5, and 6 in your notes. You should have already done the first three examples. Actually, the first number 1 and number 3. I left number 2 for you to do on your own, though I have put the answers here, 8.7 and 6.5. If you wanted to go back and check, yours may not be exactly that because you don't have a graph, and so you'd just sort of be estimating with those numbers. But those were the values that I had from computing an estimation of the height of the curve in each of those spots. So now we're going to look and we're going to estimate two things. The first one being the integral from 0 to 8. I'm sorry, you guys. I'm using a different screencaster and it's a little bit different than what I'm used to. So we want to compute the integral from 0 to 8 of x squared plus 2 dx. Now, what does that actually mean? Well, if we have an integral from 0 to 8, that means as x goes from 0 to x equals 8, we want to compute the area under the curve. Now, you'll notice that we are just estimating this value. We can't find this value exactly yet. We will be able to eventually. But that is the same equation that we had back here, x squared plus 2. We have a graph of it. And so what I essentially want to do is I want to compute from 0 to 8 this area right here. That's what that integral sign means. The integral from 0 to 8 of x squared plus 2 dx represents the area under the curve from 0 to 8. From 0 to 8, okay? Now, can we find that exactly? No, we are estimating it. So instead of using an equal sign, I'm going to use a little estimation sign, and I'm going to compute that. Now, so far, the only way I've got is I know that my left-hand rectangles gave me an area of 128, and my right-hand rectangles gave me an area of 256. So my left rectangles, those guys would have fallen under the curve, right? So I'm just going to draw one representative in here. He would have looked like that. He's obviously under the curve. And then this guy, whoops. That's kind of crazy. This guy would have been over the curve. So the way that I'm going to estimate the area under the curve from x squared plus 2 from x equals 0 to x equals 8 is I'm going to average L4 and R4 that we computed in example 1. And so that's going to give me 128 plus 256 and we're going to divide that by 2, and we're going to get an answer of 192. Whoa. Okay, so our estimate for that integral is 192 units, okay? And that's the area under the curve. So now they've asked us to also compute this guy. I'm going to use my cool rainbow pen. Check him out. Pretty awesome. Huh? So we're also going to compute the integral from 0 to 3 of g of x dx. Remember, what does that mean? That's the area under g of x from x equals 0 to x equals 3. So where is g of x? Well, g of x is this curve right back here. You may not have even done this yet, but here's g of x. We can see him there and there. And if we did some right-hand rectangles, I should probably do those in blue here so you can see them. They would have looked like this. And our left-hand rectangles, those would have been overestimates because our function is decreasing. So we're going to use those to estimate the integral under g of x, the area under g of x. And so to do that, we're going to do it just like we did before. I shouldn't use an equal sign. I'd use an approximate sign. And I'm going to say that that is approximately equal to L3 plus R3 divided by 2. L3 being 8.7, R3 being 6.5. And so that integral is going to take on the value 7.6. Okay. Now remember, this is approximate. It's not exactly 7.6. It's approximately 7.6. So this paragraph is very, very important. I'm going to read it to you. It is impossible. It's important to realize that these are only estimates for how to find the area under a curve. There is a precise way to find the exact value for the area under the curve, but our class won't cover that until chapter 6. So until chapter 6, stay tuned, it's coming. But until that time, you will either use rectangles to approximate, or, and this is kind of an important one, you can use, if you need to find an exact value, your calculator. So what we did up here was the approximation, right? We did some approximations up here. We estimated. But now we're going to work on how would we go about finding the exact value of our integral using our calculator. Okay, so I'm going to switch screens, hopefully over here, to a calculator screen. I hope that you can see that. And we're going to talk about the way that you would compute that integral. So let's go back and look at it real quick because I kind of forgot what it was. Integral from 0 to 8 of x squared plus 2 dx. Okay, so we're going to go to menu. And then we're going to go to calculus. And we are going to compute an integral. So you should see that little integral sign pop up. The integral we wanted to compute was from 0 to 8. And our function was x squared plus 2. You'll notice it automatically gives you parentheses, and we need to tell it dx. It'll always be dx for you until we start dealing with different variables. You're going to stick with a dx for now, okay? So remember, we approximated that value back here. That was this at 192, right? So let's see. I guess I probably should circle that in green here because that was my approximation. So my approximation was 192. So let's see what we get when we do it exactly. Go back, hit enter. Ooh, we got a weird decimal or fraction answer. That's an exact value. I want to see what the decimal approximation of that would be. 186.667. So 186 2/3. So the exact value of that integral you notice I don't need to use an approximation sign there. That exact value is 186 2/3. So how did we do? Well, let's see. Our last problem, we approximated at 192, and we got 186 2/3. So not bad, considering we only did 4 rectangles. So not a terrible approximation. But the only way you're going to be able to compute an exact value is going to be with your calculator, okay? Unless you happen to have a situation like example 5. So let's look. In example 5, we do not have the equation for the graph of f of x. We have a graph, but we don't have the equation for that graph. Fortunately for us, even though we do not have the equation for that graph, we will still be able to compute these guys exactly. And the reason that is that these happen to be geometric shapes that we can know. So for example, the first one we get is the integral from 0 to 1 of f of x dx. So what does that mean in real life? That means the area under the curve from f of x to the x-axis from 0 to 1. And so looking at that and computing it, these boxes are kind of annoying. You'll notice that the height of each box is actually 1.5. Crazy. So the area of each box is not 1, it's actually 1.5. Super annoying, I know. So when we're looking at this graph, we have 4 boxes of area 1.5 each. So let's see, we've got a rectangle with a width of 1 and a height of 6. And so that area under our curve right there is just going to be 6. Let's look at the next one, the area from 0 to 2. Okay, I'm going to erase my first area because now they're asking me to compute the area from 0 to 2 under f of x. Well, that's still going to be another rectangle with width of 2 and height of 6. It's a geometric shape that I know how to find the area of, and so I'm going to get an answer of 12. So what about 3? The integral from 0 to 3, well, that's going to be this box that we had before, and then we're going to tack on this triangle, right? So we know we've got 12 from here. That's the blue portion, this first part that we did. And then we need to add on this little triangle right here. So its area is 1/2 base times height. Sorry, my kid's getting a message. And I can't get over there because I've got my computer on my lap. So that's going to give us an area of 15. Okay, let's try from 4 to 5. I'll go back and use my rainbow pen for 4 to 5. Okay. So from 4 to 5, that's going to be down here. Now this is kind of a different one because if you remember when I told you, when you do an area that falls below the x-axis, holy mama jamma, they've got to stop that ringing. Sorry. If you've got an area that falls below the x-axis, that area is actually negative, right? So it's got a width of 1 and a height of -6. And so his area is going to actually be -6. Let's see, from 5 to 8, I'm going to use my, this is a cosmic pen. So it's a little different than a rainbow pen. It's supposed to look like, I think like, you know, outer space. So we want to do this area from 5 to 8. Now that's going to be this whole triangle here, right? The area from the curve down to the x-axis. So that's all of this. And so that area is going to be below the x-axis. It looks like a triangle. So the area of a triangle is 1/2. The base is, this is 3 units. And the height is -6. And so that's going to give us an area of -9. Okay, let's go back and look at from 0 to 5. Oh, this is kind of weird. So we're going from 0 to 5 this time. So from 0 to 3, it's going to look like this. Actually, I did that in green over here, right? That's that 15. So 0 to 3 is this. But then I need to continue on and do from 3 to 5. So I've got these two portions. Now this first portion that I'm doing is above the x-axis, so it's going to be positive. And this portion here, he's below the x-axis, so he's going to be negative. So my first part, I can steal that from over here. That's going to be 15, right? And my second part, that's the area from 3 to 5. So let's see, I've got a triangle here, and that triangle looks like his area, the area of just this portion right here, that's going to be -3. And then the area of this portion here is going to be -6. And so that whole area right there is going to be -9. So when I add those two together, I'm going to get a net area of 6. The area from 0 to 5 has a positive part and a negative part. They're going to cancel each other out to an extent and leave us with an answer of 6. Okay, and then last, we're going to be looking at the area from 2 to 4. This is kind of an interesting one. Let's go back to blue here. So from 2 to 4, well, I've got this part 2 to 3. That's a triangle right there. And then I'm going to go from 3 to 4. That's another triangle, but it's below the x-axis. And it looks to me like those two triangles have the same area. And so I've got a positive and a negative. So I'd have a +3 and then a -3. And that's going to give me a net area of 0. So the integral from 2 to 4 is actually going to have a value of 0 because those areas are going to cancel each other out. Okay, so our last example that we're going to look at here is example 6. And so we have got a table shown here, and they want us to estimate. Now remember, if we're being exact, we need to have a strong geometric shape, or we need to have our calculator with an equation. But here they're asking for an estimate. So we're going to be kind of back where we were before, okay? And there's lots of different ways that you can choose to estimate. So we're going to talk about that. So the first thing I'm going to do, because you know Mrs. T, she needs herself a good, oh, that's not what I wanted. I have a way to add a graph, but I can't remember. Oh, well, not worth the effort. I'll just draw it. It'll look terrible, but I'll just draw it for you. So we're going to have a table of values here, x, and then f of x, of course. And x is going to go from 0 to 12. And f of x is going to go from 20 down to 1. So I'm going to do 5, 10, 15, 20. And I'm just going to take a sec and graph all those points. So I've got 0, 20, 3, 10, 6, 5, 9, 2, and 12, 1. Okay. Now, when you look at that graph, you might be able to do that in your head, but you know, Mrs. T, she needs to have herself a little a picture so she can understand. So I'm going to think, how am I going to estimate the area under the curve from 0 to 12? How am I going to estimate that area? Well, I've decided that the way I'm going to estimate it is I'm going to do left-hand rectangles and right-hand rectangles, and I'm going to average the two. Okay, there are many different ways to handle it, but for now, we're going to stick with rectangles. So let's see, I've got 5 data points. So I think I'm going to do L4, and then I'm going to do R4, and then I'm going to average them. Okay, so I'm going to do an average of those two. So let's compute those values. Well, L4 is when the left-hand point touches the graph. And so for L4, the width of my first one would be 3, and its height would be 20. The width of my second one would be 3, and its height would be 10. The third one, of course, 3, height of 5. The fourth one, 3, with a height of 2. And so L4 comes out to be 111. Let's do the same thing with R4. So that one's going to look a little bit different. R4's rectangles, in this case, are going to be an underestimate. They still all have a width of 3. But the heights are going to be different. The first one is only going to have a height of 10, 5, 2, and then the last one has a height of 1. Remember, we ignore the first point for right. We ignore the last point for left. And so for my right-hand rectangles there, I'm going to get 54. And so when I compute my average of the two, so I am computing the integral from 0 to 12 of f of x dx, and I'm going to say that that is approximately equal to L4 plus R4 divided by 2. And L4, of course, was 111. R4, of course, was 54. And so that value, that integral, is approximately equal to 82.5.